Okay, so we were talking about Newton's method, and it's a way of coming up with the roots of an equation using the derivative to predict where the function will intersect the x-axis, and then we just do an iterative type process. So let's think about what's going on here. Basically what you're doing is you are, let me turn my headphones big up there. I must have unplugged my computer here somewhere because I'm not seeing it charging. There we go. That was when I stepped on the cord. Okay, so one way to look at this is, if you think about this, the slope of the tangent line at this point is the slope of the line between the point, our initial guess, and the point where approximating is crossing the x-axis. So what we would do is we could evaluate the first derivative at some initial value of x. So that's the derivative at this point. And that first derivative of the function, which is the slope of the tangent line, has to be equal to the same slope as this line, and the slope of that line would be, you'd have y2, which is 0, minus y1, which is the value of the function at the initial guess, divided by x, we'll call it I sub plus 1, which is our approximate intersection with the x-axis for this function here, minus the initial value of x. So if we solve this, let's multiply it out. So if you cross multiply here, you'd have f prime at the initial value of x times x sub I plus 1 minus x sub I is equal to f of x sub I. So I just drop negative f of x sub I. So you drop the 0. So this is the right-hand side. And then we'd multiply it out. So you'd have f prime of x sub I times x sub I plus 1 minus f prime of x sub I times x sub I is equal to negative f of x sub I. And then we'll move the terms that don't involve. What I'm trying to do is solve for this. What is my guess for the x-intercept? So you'd have f prime of x sub I times x sub I plus 1 is equal to f prime of x sub I times x sub I. So I'm just moving this to the right-hand side, so it becomes positive. And then I have my second term here. And then to solve, x sub I plus 1 is going to be equal to f prime of x sub I times x sub I minus f of x sub I divided by f prime of x sub I. So I'm dividing both sides by this, and you can see, though, if I can simplify this because this divided by that is 1, but I have to do it for both terms. So what I'd say is the guess for the x-intercept is going to be my initial guess minus f of x sub I divided by f prime of x sub I. So that's the process we're going to do. We're going to create a table, and the table consists of how many columns here? 1, 2, 3, 4, 5, 6. So it's going to be 6 columns, and let's say 5 rows, 6 columns. Is that right? 6 columns, 5 rows. Okay, so here it is. And we're going to put the header row for what. So this is just my iteration number. Okay, so iteration 1, which is where we start. So this just counts. And then we have our initial guess, the value of the function at the initial guess, the value of the derivative at the initial guess, the ratio of these two. So f of x sub n, I guess really should put n here. Yep, n. F of x sub n divided by f prime of x sub n. And then x sub n minus f of x sub n divided by f prime of x sub n. So all I'm doing is I'm calculating. This is my initial guess. Then I calculate the value of the function. I calculate the value of the derivative. I take the ratio of those two, which is this column, and then I just do the calculation. And that will give me my new value, and I'll put that down here. That'll be my new guess. So let's let me just let's go back to that one problem we did a couple of days ago. So I need to find the equation that we were fiddling around with when we were talking about curve sketching. And we said, there was an x-intercept, but it wasn't a rational zero. And I need the equation. So let's go get that. We'll use this as our first example. Actually, I've never done this before, so it should be fun. Well, I guess depends on how you define fun. So that was section 3.6. Okay, so this was the one that we did. Remember, I tried to guess the rational zeros and used synthetic division to see if there were any that had a zero remainder. And then we plotted the function. Ultimately, we actually went back and took the derivatives, found out where the minimum and maximums were. So we know that the intercept is somewhere around -15. Okay, so that's probably going to be our initial guess, but I just need to get the equation and actually the equation and the derivative. So let's just take both of those. Since we've already taken the derivative, we don't need to do it again. Okay, there we go. Okay, so let's just add a page and do the calculations on the right-hand side. So I'm going to guess that the initial guess is 15, -15. So if we plug that in to the function, we'll get -15 cubed. So f of x sub n, which is n equals 1, is -15 plus 12 times -15 squared minus 5 times -15 plus 20. And f prime of x sub n is going to be equal to 3 times -15 squared plus 24 times -15 minus 5. So if somebody can get their, at least a few people get their calculator out just to make sure I'm doing this correctly. As we know, I do make mistakes. And like I said, I've never tried this particular problem before, but I thought, oh, that'd be kind of interesting. Okay, so -15 cubed plus, oh, I probably didn't do negative, I probably did minus. No, I did it right. Okay, -15 plus 12 times -15 squared minus 5 times -15 plus 20. And I get -580. Anybody get that? It seems awful small, but anybody get that? -15 cubed times 12 times -15 squared minus 5 times -15 plus 20. Okay, I'm going to assume it's right unless somebody tells me otherwise. And then we take the derivative, so it's 3 times -15 squared plus 24 times -15 minus 5. So I get 310. So that's that value. So this is negative 15. This is negative 580. This is 310. If I take the ratio of those two, f of x sub n minus 580 divided by 310, I get negative 1.87. And if I subtract negative 1.87 from 15, I'll get, so negative 15 plus, basically plus 1.87, and I get negative 13.13. So that's my new guess, negative 13.13. So then I go back and redo these things. Luckily I left space in my calculation to just change the numbers. So I got negative 109 for that. So that is closer. I'm going in the right direction. And let's do the derivative. Let's see, what am I doing next? Negative 13.3. 13.13. Okay. Negative 13.13 minus 5. And so, anyway, if I do f of 13.13, I get negative 109. And f prime of negative 13.13 is negative 359. Okay, so this is negative 359. I take the ratio of those two numbers. That's not negative, it's, wait a second, something's wrong. Three times negative, oh, I forgot to square it. Okay, so error. I knew it was still negative, so I knew something was wrong. Okay, squared. I get positive. So this is wrong. This is 197. Has anybody confirmed I did this correctly yet? Yeah. Okay, good. So we take the ratio of negative 109 divided by 197, which is 0.553. So the next guess is going to be the last guess, which was 13.13, and we're going to add, or negative 13.13, negative 13.13, and we're going to add, so this turns out to be negative 0.55. So we add 0.55. So that becomes negative 12.58. So now we use that, negative 12.58. So f of negative 12.58 is 12.58, 12.58, 12.58 is negative 8.9. And the value of the derivative is plus 167. So I take the ratio of those two, negative 8.9 divided by 167, and I get negative 0.053. And so I'm going to take my old guess, which is negative 12.58, and I'm going to add or subtract a negative 0.053, and I get negative 12.53. So then you do the next one, negative 12.53. But one thing you can kind of see here, what's happening is that that's kind of gives me an idea of my error, my maximum error. So right now I'm within 5/100ths of the exact answer. And if I do it one more iteration, I'm probably going to be within 5,000ths, because you can see how the second result was negative 0.55 and the third result was negative 0.05. So I've reduced, I've reduced that by a factor of 10. And so there's no reason to believe that the next one might be within another factor of 10, which would be 0.005, which would be beyond 2 decimal points. So it demonstrates how you can get to the answer very quickly. You don't have to just do trial and error and guess and things like that. It initially didn't look that hopeful, but because these numbers are huge. F of x was negative 580, but the next time it was 109. The next time it was negative 8.9. What we're trying to do is get to 0. So let's just go ahead and do one more time. So next what we'll do now is we'll take f of negative 12.53, see what that is. What I did initially, when I put in my initial guess of negative 15, I put in negative 15.00, and that way I could go back and just change the numbers. I didn't have to rewrite the whole equation. Okay, so the value here is negative 0.56. And the first derivative is $165. So I take 0.56 and I divide by 165, and so my next change is only going to be 0.003. So when I correct this for that, you can see it's in the third decimal place. So and the reason that works that well is if we go back to the original function, which was here, and if we want to draw it now, we actually know that the actual x-intercept is about 12.5, so I can this thing actually drops off much more quickly. So this is 2, 4, 6, 8, 10, 12, 12.5 something. So there's the exact, is that right? 2, 4, 6, 8, 10, 12, yeah. So you can get that extra point, and it gives you an idea of how quickly this thing is dropping off as far as the value. So I've got a handout. Well, actually, there was that optimization problem we did the other day. Did anybody did anybody get the what the polynomial was? The ultimate polynomial. We'll see if anybody got the same answer. So somebody we'll take first. Let's see. I'll ask Asia, and then we'll see if anybody agrees with her. Did you get one? No, anybody got an answer? Multiply that whole thing out. What I'll do is if what I'm going to do is go back to last year and find out what I actually calculated it to be. Because I don't want to do it all over again. It's a long calculation. I think I did it last year. Let's see here. Section 6, Section 7, last year. Oh, here it is. Actually, that's as far as I got last time. Let me think, see if I've got it anywhere. I know I've done it before. Oh, here it is. Went too fast. So this is it. X to the fourth, when you simplify, because there was a common factor of 3, you get x to the fourth minus 6x cubed plus 9x squared plus 8x minus 12. And it turns out, in this case, it actually is a rational number. So we don't have to use the, so this was the one where the person went with the boat, diagonally to the shore. And if you multiply out, let's just go back here. Hopefully we have the same. What we ended up with, and I asked you to do outside of class, was we ended up with something like this. And then I said, go ahead and multiply that out. So what you do is you take this times that is equal to this times that, which is that. And then you just distribute the 4x squared to the left-hand side, use FOIL for the right-hand side twice. So you got x times x squared is x to the fourth, and then you have 4 times x squared, which is 4x squared. Then you go to the next one, which is x squared times, x squared times negative 6x, which is negative 6x cubed, and then 4 times negative 6x, which is negative 24x. And then you take x squared times 9, which is 9x squared, and 4 times 9, which is 36. So that's this side multiplied out. And then you put everything on one side, and so you'll have 4x squared minus 1x squared, which is 3x squared, negative 24x cubed, and then you add 6x cubed. When you move that to the other side, it gives you that. So just algebra. I divided by 3 because every one of these terms is divisible by 3, and that was the fourth order polynomial. But our only possible roots were between 0 and 3 because that was the distance along from 0 going horizontal or perpendicular initially, or you could go diagonally all the way to 3 miles. And it turns out that if you choose x equals 1, which is one of the solutions, that turns out to give you a 0 remainder, and therefore that is the one root between 0 and 3, which satisfies the first derivative being equal to 0. So we actually didn't have to. That's a solution to the problem we did the other day. If you want to just write that in there, just write this out. Say the domain is this. Do the synthetic division, which shows you that the actual solution was a integer. We could have made it a non-integer by just changing the values of the speeds by a little bit. I think one was 4, and I think the boat was 2 miles per hour, and the walking was 4 miles per hour. So if we had changed it to 2.2 miles per hour and 3.9, then it wouldn't have ended up being a nice integer. And in that case, we probably would have used Newton's method to come up with what the actual solution was, and we could have a pretty good guess. We could have picked either 1 or 2 probably, and that would have been a good start. Okay. Okay, yes, I remember what So what we have is just a example of using Newton's method to find the zeros for this equation, which is not a polynomial, but so it's, you got to take the derivatives a little harder, not that much harder. And because we're not setting the derivative equal to 0, we're just finding the value of the derivative. We don't need to, we don't need to find the root of the derivative equation. But so the first thing you want to do is you want to take the derivative of the function. So rewrite the square root of x minus 1 as x to the 1/2 power. The derivative of x is 1. And then we're going to start, I'm going to give you the initial guess, which is 1.2. It turns out, whoops, sorry. There's also, on the back is 8.0, so we're going to do it from both 1.2 as our initial guess and 8.0 as our initial guess. But let's just do 1.2. So you can evaluate the function at 1.2. You can evaluate the derivative at 1.2, and then you take the ratio of those two numbers, and then you basically subtract whatever that ratio is from the original x sub n. So let's go back to what we were just doing. So close that, we'll close that. So here's what we did. We just, there must have been a page that I stuck in here. Let me delete the page. Yeah, there we go. So yeah, we just evaluate the function. So you'll evaluate the function of 1.2, the derivative of 1.2. Then you'll add whatever, subtract that ratio from 1.2, and you'll get a new value of x. And then you'll just repeat the iteration, or repeat the process. And it says, use Newton's method to continue the process until two consecutive approximations differ by less than 0.001. So that's if x sub n plus 1 is minus x sub n is smaller than 0.001. And obviously it's going to take less than 4 iterations because I'm only giving you space for 4 iterations. So I'll give you a minute or a couple minutes to take the derivative, and then I'll do it for you. You can see if you got the same answer, and then plug in. Make sure you carry out enough decimals. So I didn't carry out, I only carried out 2 decimals, but since we need our answer within 3 decimals, you probably want to carry out an extra couple of decimals in your calculation. Make sure you got your calculation there. Yeah. Something doesn't look right. I think it's your simplification here. So you can't, this is just by itself. This is multiplied by that. So you can't subtract. I think that's what you were doing here. Just leave this in its 2 parts. You could combine it into a common denominator if that's what you're doing. Maybe that's what you're up to. You haven't done that yet, but because that should be 3, because that's 3. So if all you're doing is rewriting that, just make sure that's a 3, and then subtract 1 from the thing. So did anybody get that for the first line numbers, just to make sure? Okay. So if you can't get those, raise your hand and I'll come and look at what you might have done wrong.
Do you have to go all the way up, or can you round, or does it need to be?
Yeah, because they wanted the answer to 0.001, I ended up, probably this case you didn't need to take as many significant figures because the change was large. But once you get to more further down here, you're going to have to carry up more decimals. What I did was I put in 1.2000 into my equations so that I could go back and change them to that many decimal points. 1.1398. So actually, I only took 2 iterations because if you look at the third iteration, my change was only going to be 0.0001, which is to the 10. Is that 10 thousandths or 100 thousandths? Let's see, 10th, 100 thousandths, 10 thousandths. So it's within to 0.0001. So the answer 1.1458 is plus or minus 0.0001. So that one is already, the second time we did it, made it within 0.001. So let's do the same thing for the same equation. So you've already got the functions. You just need to go on the back and start with x sub n initially as being 8. and see what you get with that. So you can go back and change your equations. Just put 8.00. Actually, that one's even going to be quicker, I think, because my initial guess was really close. And I wrote ratio in there because I couldn't have enough space to write the equation that you have there. I'll let you do the next row, but I think based on our experience last time, we might be able to just have one more iteration, maybe two at the most. One thing is the slope is not as great. If you look at the one over there, the slope is 2.3, so it's fairly steep, and therefore the ratio of the two was 0.06. Here it's 0.145. So even though it looks like it's initially a even though the value of the function is a little bit closer to 0, it's because the slope is not as high, it may still take more than, it may take another iteration. Actually, just took one more, because when you use your first new guess and you calculate the derivative, you take the value of the function. The value of the function is 0.0004, which is close to 0, of course. And then the value of the derivative is close to the original one, because it's not that much different in terms of x, so it's negative 0.427. And take the ratio of those two, and you get 0.0009, which is close to 0.001. So once I've made that correction, then the next correction will be in the who knows how many decimal points. So I get 7.854. So let's plot this function and just show you how good we are at predicting the intercept. So the function was 3 times square root of x minus 1 minus x, and if we plot that, it looks like that. And we got to zoom out a little bit in the x direction. So you see it has two x-intercepts, one here, which was our initial one, and here. And we would have known that because we might have figured out where the derivative equals 0 was here, and so we would have known that this was a maximum, and it had to go through somewhere on the x-axis here, and had to go somewhere on the x-axis there. So we would have known there were two roots. And then what we'll do is we'll just zoom in on these. If I keep zooming in with this graphing program, we'll get more and more accurate results. And then I put my cursor right over top of that. And so it says my x-intercept is 1.1458. And what do we get? Pretty close to that. 1.1458. There it is. Okay. So that's good. And then if we zoom in on the other point, so we just keep zooming in a few times, and every time you do that you get more accurate results. So then I put my cursor right here, and it says it's 7.8542, which is 7.8542. So there we did it. That's pretty good. But it actually it's very good at demonstrating how quickly you can come to the x-intercept. If you did it the other way to do it would be to look for where the function crosses the x-axis and then kind of interpolate between those two. And it wouldn't take that long, but it would certainly take longer than using calculus to figure that out. So here's your problems for section 3.8, 6, 9, 13, 15, 22. So you can see the procedure's not that difficult. You've just got to make sure you get the derivative correct, and then you plug it in your calculator correctly. What time is it here? Oh, it's almost time to quit. Okay, so what we'll do tomorrow, remember, calculus test is next Monday. Sections 3.1 through 3.5, 3.7. There will be a take-home for section 3.6. And what I'll do is actually, instead of making it due Tuesday, I may make it due like Thursday. So you'll have a couple of days to work on the take-home portion, because that way I can make it more difficult. And you have a few more days. You can powwow in study session, something like that. But I will I'll have Mr. Watkins hand it out after the test, so you can work on it during that time that you have remaining after you've taken the test.